This week we have the last 3 lectures planned today, tomorrow and on Thursday. And on Friday it's a kind of open slot for a lecture if you want to see something still or to see some examples, some overview. Then I can do it in that lecture, for example. You can send me requests if you have specific requests for it. We are now in the middle of the analysis part of the whole course. We did one lecture on Friday where the analysis was inspired by the social network analysis area and was mostly focusing on a kind of static analysis of network structure. But now we will have 2 lectures today and tomorrow that focus on the dynamics of the behavior of network models. So that's the focus, and I cover now from the 2016 book 1, chapter 12, most parts, and also part of the 2020 book 2, chapter 11, that you can find it back also there. So the idea is that usually dynamic models are not so easy to find out what behavior they will have. So in many cases, it's just that people do a lot of simulation experiments and then find out in an experimental way what the behavior is and how it may depend on certain characteristics of the network model. But in some cases, for some types of properties, you can also find in a mathematical manner, based on the network structure characteristics, what the possibilities are for the behavior, what the type of behavior there will be, or at least some properties of that behavior. And then, if you do that, then you can compare that to the results of simulations. And then you have a possibility for verification of your model. Verification means that you check whether it has the properties and behavior that were expected. So that's a good thing, because then you can have an additional say that you are a bit more sure about that the network model that you have is okay, is good. And that's also good for having a better foundation of your model. Also, if you go for the publication, these things also help for reviewers to get confidence in your model. So different types of behavior are possible. Examples that can be analyzed, but can be, it depends a bit on which type, how well that can be. Stationary points or equilibria, that's what we will focus on mainly today. That's you can analyze that well. Monotonicity, you could also analyze that in principle, although we don't have really attention on that, but you could do that as well. But there are also 2 other types of behavior. You may have seen in one of your example models already limit cycle behavior, when it ends up in a repeating pattern behavior. Like for example, for the emotion regulation example, then that easily can occur, that you regulate your emotion, but after you regulate your emotion down, then your control will stop and then the emotion can come up again, and then that can repeat forever. But you can also have even not such a pattern, but a chaotic behavior. Now, the last 2 types of behavior that do not really fall under this word can here. You could do something on that, but it's usually very difficult. So we will not do that in this course. So I will illustrate some things by this example, the ice cream example that you still will know. That you see some ice cream on the other side of the street and you can buy it, can go there to buy it. So in an example simulation of that model is this. And I will point here at some stationary points. Stationary points are just where the graph is flat for a certain curve. For example, this is a stationary point for the blue and for the gray line, also of the red, of course. And this is for most lines a stationary point here. And also there is one for the blue and the gray line. And also here for more other lines that are stationary points. So that's the idea, the points where the graph is flat. And of course, if the model finally gets a kind of stable situation, then that's also a stationary point, because then all curves are flat. That's what you call an equilibrium. These are also examples in a limit cycle behavior. So also for limit cycles, you can still do the stationary point analysis. So because then you have all these tops and dips. So everywhere you can find these things at many places to analyze whether they are okay, whether the model is correct for them. So therefore, you can do at least something for limit cycle behavior, but you cannot predict exactly how these things will go, and also the period is difficult to predict how long this will be. One famous example, of course, that we have used more times already, that's this sheep example. And note that here there are two types of behavior that are occurring. The one type is that the network structure ends up in a cycle, a cyclic network structure, and also the behavior ends up in a limit cycle behavior. So there is a cyclic structure and a cyclic behavior. These are two different things, and that is also, we will also address that, the difference between equilibria for the base level, for the base network, but also equilibria for the adaptive structure of a network. So these types of things will be addressed. So let's see how we can do. I give some definitions now. A stationary point, that the curve is flat and the derivative of the function is 0, or if you have a very small delta t, then the next point is at the same level as the previous point. That means indeed that the graph is horizontal. In most cases, it can be a local maximum or a local minimum of the function at t. That's how you can mathematically describe it. Now we have this difference equation. When I discussed that in the beginning of the course, I said you will not often see it anymore because it's hidden in the software environment. That's indeed true. But now this is only one moment that we still have to come back to it to look a little bit better. So when would there be a stationary point? That means that these two are equal. So that means that this whole thing should be 0, this part. And this 0 means that either your speed factor is 0, which is a bit exceptional, it can be, but it may not often, or this has two equal values. The aggregated impact is exactly equal to the y. So then we have this criterion. This is the criterion of a stationary point. And that criterion can be checked. You can just calculate this aggregated impact for a given simulation and using the values at a certain time, and then compare it to the value of this y at the same time point. So that's one of the methods that I will discuss today. So let's see this. If we exclude the speed factor, that's 0, that we assume it's non-zero, then it's just this equation that you can consider, and that's the stationary point equation. And if for all states of the network, all y, this holds, then we call it an equilibrium. So then it holds for every state. And then you call these equations equilibrium equations. So that's our starting point for analysis, these equilibrium equations. And we can do many things with them. So what we do now is to have a number of properties of the network structure. This is the conceptual representation, like in the role matrices, for example. This is then the numerical representation in terms of the difference equation. But then you can look for properties of the network structure and properties of the behavior that relate to these basic things, and then see whether there is some relation that these properties of the network structure entail or imply in a certain way the properties of emerging network behavior. That is what we look for mainly in this lecture. So you can need, if you want to really do more theory about it, you need you need to have mathematical definitions of them, but I will not go into detail in many cases. I will just show a few of them, small number. So that's now the interesting challenge, the arrow in the upper level, how can that relate to each other? And the structure is defined in terms of these characteristics of connectivity, activation, timing. So that's the challenge now, to find such properties. So this is also one of the examples that you have seen earlier, but now we consider them from the analysis perspective. So whether this is a flock of sheep 1 or 2, it depends on the structure of the network. And maybe in this case, the structure should suggest that it's not 1, and it will just go to different directions. So we will have some background now to explain why that is the case. So this example, you have seen it already in one of the in the opinion dynamics assignment. There are different behaviors possible, and this is the logistic function. So that has that behavior. This is the scaled sum with normalized functions. Then this happens, one value. And this case happens when you have two constant. You have seen this also in the opinion dynamics assignment. Then there is also a division. The people get divided like there, but in a different way. So these types of behaviors we will analyze now a bit more in detail. So there is one theorem that there are in the book a number of theorems in the 2020 book, in book 2. I have one here and later another one that is not exactly one of the theorems, but just is a summary of some properties. So theorems are like this. They have some conditions on the characteristics of the network, and then you get, say, a behavioral property, what is happening in such an equilibrium. So then, in this theorem says, if the network is, every state is reachable from all other states, except at most one state, and the combination functions have some properties, and normalized, strictly monotonically increasing, and scalar free. I will show that a bit later. Then in an equilibrium, all states have the same value. So in this case, we can explain the middle figure, middle graph I just shown before. That it depends on these types of properties. So the network was fully connected in the case, in the example, so that's indeed fulfilled there. And the function, it turns out that also the scaled sum function satisfies these properties. I will show them. If you don't have this, if there is more than one state, you know there is a kind of saying, 2 captains will sink the ship. So if there is two states that are not affected by other states, then you will have a problem, and this will not be true. So that will mean sink the ship, means that there will be not any agreement anymore about opinions. There will not be one opinion, but there will be several opinions then. I will come to that later, to that case, that there are more than one captain, but here one captain is allowed or no captain, so that both are fitting in this theorem. So this explains, this is an analysis that shows that in that case of the middle case with the scaled sum function that's normalized, that you should have one value finally. If you have a simulation yourself and it is not one value, it has different values in the end, then you know something is wrong because it contradicts this theorem. So that's how you can use it to verify things for verification. So this is at most one captain, and then we will see later what happens for no captains, because there is also a theorem for that. So normalized, we already know it, that you mean that you can do that by having a scaling factor that is the sum of the connection weights. But the general principle is that if you apply the combination functions to just only once, then it should return 1 as a value. Monotonic, I think that's, you can imagine that means that if you take higher values in it, then the value of the function should also be higher. This is not strictly, then strictly has an additional condition that if one of them is strictly higher, then also the value of the function should be strictly higher. These properties are satisfied by the scaled sum also by the logistic, but not the last one. Scalar free means that if there is you multiply all incoming values by, for example, 0.5, then that results in a 0.5 lower function value. So that's so that the aggregated impact also becomes 0.5 lower. That property, the logistic function does not satisfy this property, but the scaled sum, Euclidean function, the number of functions, these functions satisfy it. So the scaled sum, they satisfy all these properties. Euclidean function also, and also the scaled geometric mean functions. I may not have shown that earlier. That's this one. You know maybe what is geometric mean is. That's you take the product and then the roots for the number of them. But here in this case, we have a scaling factor still, where you can also use the normalization by that. So these types of properties of the functions are okay to satisfy this theorem that I have shown. Notice that this is a linear function, this is not linear, and this is also not linear. So that means that the distinction, the borderline, is not between linear and not linear, but it's within the nonlinear functions somewhere. Some linear functions, not linear functions belong to this category, and others may not belong, like the logistic function. So you can always apply this theorem for these functions, these types of functions, but not for the logistic functions. So that's now we have the explanation. This does not come to one point, not one common opinion, because the function is not scalar free. This just come to one value because it satisfies all three properties, and this one does not come to one value because we have two states that are not reachable, and only one exception was allowed. So that makes that these things now can be explained by such an analysis. So this is the two captains situation, and the two captains situation is not covered by this theorem that I've shown. So this case is that one or two flocks, not one flock. If there are two captains here. So they will lead to different directions, and all sheep will be divided between them. If there is only one influencer, then it would be one flock. But of course, in this case, we had just two. So this is also what you have seen, I think, in the opinion dynamics assignment. If you have two states that are constant, you take speed factor 0 for two of them, and then all of them will go in between them. That is at least something. So if you have two captains, then the opinions of the other members will be somewhere between the two captains. Not the same value, there will be different values again still. And also here, if you have low values for the two captains, then, so these are two captains that are not equal, but then still in the direction where they are, it's still chosen by everybody. So that's another theorem that can explain this. And this is the, say, the multi-captain theorem. Suppose now that you have the connectivity condition, so every state is reachable except a number of independent states. So these are not influenced by any of the other states. They are, say, the captains that are never listening to anybody. An arbitrary number. And you have the same aggregation condition, so the function should still have these properties. Then in an equilibrium state, if the independent states have a range of values in equilibrium, say between 0.5 and 0.8, then also every state has that value between these limits, between these bounds. So that was indeed, this explains the previous graphs that shows that indeed if the captains have values, like in this case, values 0.85 and 0.9, then everybody should have in the end values between these two values of the captains. And also here, in the end, they should be in between that. So now we also have a theorem that explains that type of behavior. And again, if you have a model that does not show that in a simulation and the theorem says it should show, then you will know that you have to check whether there is some error somewhere. So these are just two theorems that I want to show now, and most of the things I'm doing today will occur in assignment of tomorrow. The assignment, what is it, 9 I think, and in the basic part. Tomorrow I will have a lecture where I address the things that are in the advanced part of that same assignment. So if we look now back at this, if there is only one, then this will be one flock, and for the two cases it will be two and in between, but now with one it will be in one direction. So therefore that makes clear, according to these theorems, what will happen. So let's now consider this for the other example too, the ice cream example. The stationary point equation is like the SS state is the omega of the sensing times the world state values. So you have this equation, and this is the aggregated impact, or the single impact in this case. It's only one impact. And then we have this equation. For the next step, from sensor state to sensory representation state, we again have such an equation, another equation. It's also the aggregated impact equal to the value. So you can use such equations in two different ways. And the first one is verification through substitution of values. In these equations, you can substitute the values that you see in your simulations, or you can solve these equations and compare them, the predicted values, to the simulations. So these are the two different ways. The first one can always be done because you can always substitute values. The second one depends a bit on the type of function because not every function can be solved so easily. Like the logistic function is a bit difficult to handle in that way, but it still can be handled like this. So I will just show first the substitution one. You could generate a simulation for a number of states, identify stationary points with their time points and state values. And then for each of these points, take the values of the states that are connected with an incoming link to y. At the same time point, it's very important that everything is at the same time point, all time points t. So you consider both that value and these values. Then you substitute all of them in this equation. You substitute the x1 till xk values and the y value here, and these are just known network characteristics. You can also take them from your role matrices and fill it here. And then you check whether it's true or not, or how close it is to being equal, because in the realistic case, it's never exactly equal, but it can differ like 0.01 or 0.001, something like that. And that's good. If it would differ 0.2, then it would not be good because it's a big difference. So if the equation holds with an accuracy, for example, of this, then the test succeeds, otherwise it fails. And then if it fails, you have to do some work because you have to find out where is the error, because then you have to solve this problem. So that's the first approach. We use such a table for it. This table is also shown in the assignment. You select states. There can be columns for states, or maybe more columns for one state if there are more stationary points for it. Then you indicate for the maxima, for example, the time points and the state value, and the aggregated impact that you will calculate like I've shown, and then the difference between the two. That's what you fill in all these cells. And also for the minima, then you get such a table with numbers everywhere, and then you see that these numbers have small differences, like 0.005 here or here, 4. And so these are small differences, and then you are a bit happy because that does mean that you don't need to do extra work because now it's okay. Also, these are fair numbers, they are okay. But if these differences would be much higher than like 0.3 or 0.5 even, yeah, then you know certainly there is something wrong and you have to find out what. So that will be asked also for the assignment, the basic part of that. So these are the things that should succeed, and if you fail somewhere there, then that needs further inspection. So the next, the other method is by solving the equilibrium equations. And then you consider them, all the equilibrium equations. Then you leave out the t, and you make some separate variable x in it for all of them. And then you have an equation in a number of x's. So there are as many equations as there are states in your network, so that can be a bit high, but you can also look at each equation separately. So then equilibrium is a solution that fulfills all these equations, a solution of all these equations. And then after you have solved them, you have found values of all states in terms of for example, connection weights or other parameters of your network, other characteristics. So then you already have a prediction of what the outcome should be, and then after that you can generate a simulation, and then check the equilibrium values in the simulation, and then compare them, and then again, if there is a difference that is too big, then it fails, otherwise you succeed. And then the same step has to be done, that you have to solve this issue if there is a failing. So these things will be addressed in assignment 9 by the substitution will be addressed by the substitution method by Q1. Solving the equations will be done in question 2 in assignment 9. And for adaptive networks, the solving will be done in question 3. I will show that in a minute how you can do that. The solving of the equations can be done by support of a tool that I will also show now. So let's consider these equations again. We have this equation, we have this equation for the example, and then for this equation for the preparation state, that is a scaled sum of these things. And then you have this equation. So this is the set of equations. These are all linear equations. So therefore we have the possibility to solve them, especially because there are also tools to help you. So let's see how you can do that. These are for the adaptive ones, but that will be in some more detail here also. Let me do that first, and after that I will do the linear ones. So this, you can see how you can do this by hand. Remember that the simple linear homophily function was this one, and then an equilibrium equation is that it should be equal to the W itself, because it should be stable in a stationary point. So that means that you have this equation where this can be left out, and then you have only this one. And this is a product of three things. And if this should be 0, then only that can happen when one of them is 0. So therefore, you have the following solutions. W is 0, W is 1, or the difference is exactly the tipping point. This is very exceptional that it can occur, but it can occur. So be aware that you also should consider this as an option. But in many cases, this happens. And that explains that often in society, segregation takes place when there are groups with high connections and between them low connections, or clustering, or community formation, or similar types of phenomena that are indicated by such words. Another example is the Hebbian learning. Both of them will be done in the assignment 9, question 3. Then we can do it as follows. We can have this function, and that should be W with some rewriting you can find this relationship. By the way, you can just use these relationships in the assignment. You don't need to derive them yourself because you can already copy it from here if you want even. So you can just use this and then check whether this is fulfilled for the simulation that you make. And for example, in this case, if the persistence is 1, that means full persistence, then that means that this is 0, this part, and then you have this divided by that one, and that is 1 as long as these are not 0. So these types of conclusions can be drawn about that. That will lead to the full value 1 of your connection for Hebbian learning. If the mu is not 1, lower than 1, then you can never get the full 1. It will always be a bit lower. That also follows from this formula. So that's the adaptive functions, the functions for self-model, say, and that will be addressed. Now back to the linear equations. Suppose this is a linear scale sum function, this is linear. Then these equations are there. And you can rewrite them a little bit by multiplying by the scaling factor, then is this one. Now we have a nice tool for it to solve such equations. So you will also do that in assignment 9 in question 2. Just use this equation to solve this solver to solve your equations. In a symbolic way, you can use it by still having this as not numbers but parameters that are not yet filled. You can put also numbers, then you have just the number as an outcome, numbers. But you can also have expressions, and that is done here. So this is how it looks, this Wim's linear solver. Here you just paste your equations, you copy them from your text editor, you just paste them there. Be careful that it doesn't understand Greek letters, so you have to replace like omegas with W. But for the rest, it accepts subscripts as normal, and even if there is no multiplication sign, it will create itself usually. Then here you have to add the parameters. So there's ones that are not variables that are solved. So the parameters are like the omegas, the lambdas, those types of things. So this is the idea, to use it like this. And you will do that. And for example, if I do it for these equations, then it goes like this. Then it shows this. I replace the omegas by the W here, as you can see. And it rewrites the equations now to make is 0 of them. And I added this equation to have an indication of the stimulus that's coming in. And now it gives a solution. It gives this solution. It gives an expression for the preparation state in terms of all these connection weights and in terms of the level of the stimulus and also of this one. And of course, the stimulus itself has the same level. So it just gives a formula. And these are a bit impressive things if you can just have that and you include it in your paper or leave it on your screen when your parents are visiting you, just to show how serious your work is. So that is a relatively easy way to get rather complex expressions that you can find. Of course, you can also put just numbers at these places. Then you also have numbers here. And then you can also a number here, for example, for a specific case. Then you get only numbers. Then you get the numbers for all of them. So that's also what you will be asked to do in the assignment of tomorrow, question 2. And I think this is almost the end. Yeah, I think the last 6 slides show how you can also use the linear solver to address functions like the Euclidean function by making the powers a new variable y, and then solve that equation in y, and also for the function, the geometric mean function. But I don't think it's needed to show that to everybody. If you ever want to use that, remember that these 6 slides are here, and you could you find how you can use that. So for now, I think this is enough for the preparation also of the assignment tomorrow. Is there any question for now, maybe?